Hello, everyone, and welcome to Chapter 3 now. We are going to start a new chapter here, and the main feature of Chapter 3 is something called the derivative. If you've ever talked to anyone who's taken calculus, or if you've taken some calculus yourself in the past, you might have heard of this thing because the derivative is one of the main features of calculus. So in section 3.1 here, we're going to kick it off with a little refresher on tangent lines, and we're going to connect those to this new thing, the derivative at a particular point. So first off, a little bit of recap. Let's recall from section 2.1, how are the slopes of secant lines and tangent lines related? And if you remember, we would find the slope of a tangent line. Okay, slope of a tangent line. This is what we considered the limiting case of a bunch of secant slopes. So the slope of a tangent line is the limiting case of the secant slopes through a point. Right, so that was when we did that whole thing with making a secant through two different points, and then we would let one of the points approach the other, and they would get closer and closer and closer until it was just at a single point, and then that was our tangent line. So the slope of a tangent line is the limiting case of the secant slopes through a point. And what that looked like was something like this. All right, here's a little function here. Along our x-axis, we're just going to focus on that one single point. So instead of calling this like x1, as in, we in the past had x1 and x2 for the two different points, since we're really only just looking at one point now, we are going to just call that x sub 0 or x naught. All right. And then our other point, I'm making little quotes right now, the other point for the secant slopes is just going to be based off of x naught. We're going to let it be some little distance away called h. And so this point over here is at x naught plus h. Okay, so those give us our 2 points on the function curve. Okay, so this right here would be f of x naught. This up here would be f of x naught plus h. This is for f of x there. And so what we would do is we would let those 2 points get closer and closer to one another. So we'd bring x naught plus h closer and closer in towards x naught. And originally we would have had a secant through those 2 points. But then as x naught plus h approaches x naught, that secant will get on 2 points that are closer and closer together until we hit the limiting case of closeness, the 2 points being right on top of each other, right at x naught, and then we have a tangent line there. So that's what we are refreshing here. Okay. So if you'll recall, the slope of a secant line, when we were just trying to focus on one point, we would say would be f of x naught plus h minus f of x naught over h. Okay, now where that was coming from is that the h on the bottom here, that is the distance between the two x values. So we could say x naught plus h and then minus x naught. That way you can see like the classic slope formula here. This is like y2 minus y1. Here's x2 minus x1. All right. So that's where that all was coming from. But then down in the denominator there, that just simplified down to h for us. So we would usually just write it like this. F of x naught plus h minus f of x naught over h. And yeah, in chapter 2, we were using x1 instead of x naught. But in chapter 3 here, the book makes a little bit of a pivot and they're going to call that x naught instead. No worries, it's going to behave the same way. All right, so that was our secant slopes. And then, if you recall, how we would find the slope of a tangent line from that, we would put our values in here and we would do some calculations and simplifications, but the end step here was to let h approach 0. So to find the slope of a tangent line, all we're doing there was letting h approach 0. So we were taking a limit as h approaches 0 of that expression that we just wrote. F of x naught plus h minus f of x naught over h. Okay. And that was the deal for finding the slope of a tangent line. Now, we also get another fancy little name here for this part of the expression, that f of x naught plus h minus f of x naught over h part. That is something called the difference quotient. Okay, difference quotient. Now, this isn't a term that gets used a heck of a lot, just here and there, but it is nice to know. And it does also help you sometimes remember how to set up this formula. Because sometimes, you know, when you're doing this from memory at the start, it can be hard to remember maybe where your plus goes, where your minus goes there. So the fact that this is a difference quotient helps you set up the main features of this formula. Difference means subtraction, so there's a big subtraction up in the numerator. And then quotient means division, and ultimately, yes, this is a division type of formula. So we got our difference quotient there.